There is a galaxy so enormous that if you placed it where the Milky Way sits right now, it would swallow Andromeda whole. Not approach it, not brush against it, swallow it and still have room left over for every other galaxy in our local group. Its diffuse halo of ancient starlight stretches across 4 million light-year of space. And it contains approximately 100 trillion stars. All of them old, all of them slowly dying, all of them bathing the cosmos in a faint golden light that has been travelling toward us for over 1 billion years. But here's the part that genuinely disturbs astronomers. This galaxy might not even hold the record, because the answer to what counts as the largest galaxy depends on a question nobody can answer cleanly. If you enjoy journeys into the most extreme corners of the cosmos, consider hitting that like button and subscribing. It genuinely helps this channel keep making content like this, and I appreciate every single one of you who takes the time. Now, let's begin. Before we talk about the largest galaxy ever found, we need to talk about what a galaxy already is, because the word has become so ordinary, so familiar, so casually tossed into sentences about space that most people have completely lost contact with what it actually represents. A galaxy is not a picture on a poster. It is not a thumbnail in a documentary. It is not a glowing smudge you scroll past on a science website. A galaxy is a gravitationally bound collection of stars. Gas, dust, and dark matter so vast that even describing its size requires units of measurement that themselves defy human understanding. And until you feel that, until you genuinely sit inside the weight of what a single ordinary galaxy represents, there is no way to appreciate what happens when galaxies grow beyond anything ordinary. Start with the Milky Way, our galaxy home. Every star you have ever seen with your naked eyes belongs to it. Every constellation, every planet, every meteor shower, every sunrise caused by a local star sitting 26,000 light-years from the galactic centre. The Milky Way spans roughly 100,000 to 200,000 light-year from edge to edge. Depending on how you define its boundaries, that is not a small range of uncertainty. The difference between these two numbers is itself 100,000 light-year, which is already an almost incomprehensible distance. But for the purpose of building a sense of scale, take the conservative estimate, 100,000 light-years across. 1 light-year is the distance light travels in a single year, moving at 186,000 ms. In 12 months of continuous motion at that speed, a photon crosses roughly 6 trillion miles. Now multiply that by 100,000. The Milky Way stretches across approximately 600 quadrillion miles. Writing that number out produces a string of zero so long that it stops meaning anything almost immediately. But here is the part that matters more than the number. If you could somehow stand at one edge of the Milky Way and fire a beam of light toward the opposite edge, that beam would not arrive for 100,000 years. When the photon left, human beings had not yet invented agriculture. By the time it arrived at the other side, assuming we survived, we might be unrecognizable as a species. That is the width of a single average galaxy. One beam of light, 100,000 years, just across the thing we live inside. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each of those stars is a nuclear furnace, some far larger than our Sun, some far smaller, scattered across the spiral arms and the central bulge and the sparse outer halo in a distribution shaped by billions of years of gravitational evolution. Most of these stars likely host planets, Recent estimates from the Kepler mission and subsequent surveys suggest that nearly every star in the galaxy has at least one planetary companion. That means the Milky Way alone contains hundreds of billions of worlds orbiting hundreds of billions of suns. And we've explored exactly one of those worlds in any meaningful sense. That is our galaxy. That is the baseline. That is what we already know is vast beyond imagination before a single comparison has been made. But here is something about the Milky Way that makes its enormity even harder to absorb. Despite containing hundreds of billions of stars, the galaxy is overwhelmingly empty. The average distance between neighbouring stars in our region of the galaxy is roughly 4 light-years. That is the distance between our Sun and the nearest stellar neighbour. Proxima Centauri, 4 light-years of essentially nothing. If you shrank the Sun to the size of a tennis ball, the nearest star at the same scale would be another tennis ball sitting roughly 1,200 m away. Everything between them would be vacuum. Emptiness so complete that a spaceship travelling through it would encounter functionally 0 atoms per cubic cm for most of the journey. The galaxy is not a dense swarm of stars packed tightly together. It is a scattering of tiny luminous points separated by abysses of nothingness so wide that even light, the fastest thing in the universe, requires years to bridge them. All those hundreds of billions of stars exist inside a structure that is almost entirely void. The galaxy is enormous not because it is full, but because it has to be enormous to contain so much emptiness between its scattered points of light. This emptiness has consequences that reach beyond aesthetics. It means that any civilization arising on a planet orbiting one of those stars is profoundly structurally isolated from every other star in the galaxy. The nearest potentially habitable world might be tens of light-years away. A radio signal sent from Earth to that world would take decades to arrive, and a response would take decades to return. A spacecraft travelling at any speed humanity has ever achieved would require tens of thousands of years to make the crossing. The galaxy is filled with stars, but the spaces between them enforce a loneliness so deep that it may be the primary reason we have never heard from another civilization. The silence of the cosmos is not mysterious when you understand the distances involved. It is the expected consequence of a galaxy that is mostly made of nothing. Now, here's the thing that begins to crack the foundation. The Milky Way is not special. It is not particularly large. It is not particularly small. Among the 2 trillion or so galaxies estimated to exist in the observable universe, the Milky Way is actually larger than the vast majority. Most galaxies are dwarfs. Ours is a reasonably massive barred spiral galaxy with a moderately active history, a decently sized, supermassive black hole at its centre weighing roughly 4 million solar masses and a set of spiral arms that mark it as a respectable but unexceptional member of the spiral galaxy class. If galaxies were people, the Milky Way would be tall enough to stand out in the general crowd, but utterly unremarkable among the other tall figures in the room. Nothing about it would draw special attention. And yet, this average galaxy already contains more stars than any human being could count in a lifetime. More planets than there are grains of sand on an entire continent, and more empty space between its stars than most people can psychologically tolerate thinking about. The average is already terrifying. What happens when we leave a varage behind? Look toward the constellation Andromeda on a clear autumn night and find a faint smudge of light that ancient astronomers once catalogued as a nebula. That smudge is the Andromeda Galaxy, our nearest major galactic neighbour. sitting approximately 2.5 million light-year from Earth. The light reaching your eyes when you look at Andromeda tonight left that galaxy before modern humans existed. You're seeing Andromeda as it appeared when our ancestors were still learning to chip stone into tools. And what you're seeing is a galaxy significantly larger than our own. Andromeda spans roughly 220,000 light-years in diameter, more than double the conservative estimate for the Milky Way. It contains approximately 1 trillion stars, which is at least 2.5 times and possibly 5 times the number in our galaxy. Its supermassive black hole is more massive than ours, weighing in at roughly 100 million solar masses. Andromeda is not just a neighbour, it is the dominant galaxy in our local group, the gravitational family of more than 80 galaxies that includes both the Milky Way and Andromeda as its 2 largest members. For most of human history, we assumed our galaxy was the big one. We were wrong. Andromeda outweighs us in stellar count, outreaches us in diameter, and outshines us in sheer visible mass. If the Milky Way and Andromeda were siblings, Andromeda would be the older, larger, more imposing one, and we would be standing in its shadow. The 2 galaxies are falling toward each other at roughly 250,000 mpc in approximately 4 to 5 billion years. They will collide, merge, and form a single massive elliptical galaxy that astronomers have already nicknamed Milka. During that merger, the spiral arms of both galaxies will be destroyed. Stars will be flung into new orbits. The overall structure will transform from 2 elegant spirals into a single diffused blob of stars, moving in chaotic paths around a shared centre of mass. The merger will not destroy individual stars or planetary systems, because the distances between stars are so vast that direct collisions are extraordinarily unlikely. But the galaxies themselves as structures will cease to exist in their current form. 2 trillion stars rearranged into something new. Now pause and feel the scale of what has already been described. The Milky Way is 100,000 to 200,000 light-years across, and contains hundreds of billions of stars. Andromeda is 220,000 light-year across and contains 1 trillion stars. These are the 2 largest galaxies in our immediate cosmic neighbourhood, and the distances between them are so vast that light requires 2.5 million years to make the crossing. The local group that contains them both spans roughly 10 million light-year. Every observation we have ever made of the deep universe has been made from inside this system, from a single planet orbiting a single star in the outer arm of the smaller of the 2 dominant galaxies. And here is where the discomfort begins, because even Andromeda, as massive as it is, as dominant as it is within our local group, is not remotely close to the upper limit of how large a galaxy can become. Not close. Not even in the same conversation. Andromeda is a large spiral galaxy. Yes, but the universe contains a category of galaxies that makes spirals look modest by comparison. These galaxies are so enormous that astronomers had to invent special terminology just to classify them. They sit at the centres of galaxy clusters like monarchs at the heart of an empire, and they earn their size through billions of years of the most violent process in galactic evolution. They are the product of cosmic cannibalism on a scale that is difficult to overstate. To understand what these galaxies are and how they got so large, you need to understand what a galaxy cluster is and what happens at its centre over cosmic time. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of individual galaxies, all held together by the combined gravitational pull of visible matter, hot intergalactic gas and enormous quantities of dark matter. The Virgo cluster, the nearest major cluster to our local group, contains over 1/300 galaxies and lies roughly 54 million light-years away. Larger clusters like the Coma cluster contain thousands of galaxies and span tens of millions of light. At the centre of nearly every large galaxy cluster sits a special type of galaxy. Astronomers call these brightest cluster galaxies, or BCGs. The name is descriptive. They are almost without exception the brightest and most massive galaxies in their respective clusters. They sit at the gravitational bottom of the cluster's potential well, meaning they occupy the point toward which everything else in the cluster is slowly falling. Over billions of years, smaller galaxies spiral inward through a process called dynamical friction, losing orbital energy and sinking toward the cluster center. When they arrive, the BCG absorbs them. It strips their stars, swallows their gas, and incorporates their mass into its own growing body. This process has been happening since the galaxy cluster first assembled, and in the oldest and most massive clusters, the central galaxy has been feeding for the better part of cosmic history. The result is a type of galaxy classified as a CD galaxy. The lowercase c denotes supergiant. The uppercase D refers to a diffuse stellar envelope, an enormous halo of stars that extends far beyond the galaxy's visible core. These halos are not sharp-edged or well defined. They fade gradually into the surrounding space, blending almost imperceptibly into what astronomers call intracluster light, the faint glow of stars that have been gravitationally liberated from their parent galaxies and now drift freely through the cluster's shared gravitational field. Where the galaxy ends and the cluster begins is not always a clean distinction. The CD galaxy has eaten so many neighbours and spread its stars so far that its boundaries become genuinely ambiguous. What distinguishes CD galaxies from ordinary elliptical galaxies is not merely size but structure. A normal giant elliptical like Messier 87 at the centre of the Virgo cluster follows a brightness profile that decreases smoothly from the centre outward according to well-understood mathematical laws. At some radius, the brightness drops below detection thresholds and the galaxy effectively ends. A CD galaxy follows a similar profile in its inner regions, but at a certain distance from the centre, the profile flattens, instead of continuing to fade. The brightness levels off and extends outward in a diffuse, extended envelope that refuses to end neatly. This envelope is the signature of a galaxy that has been built through mergers. Each consumed galaxy adds stars to the outskirts, building up a halo that grows more extended with every meal. The envelope is the archaeological record of billions of years of galactic cannibalism written in starlight. These CD galaxies are the largest visible galaxies in the universe, and they represent something fundamentally different from the spirals and ordinary ellipticals that make up the bulk of the galaxy population. They're not simply big versions of normal galaxies. They're gravitational end products. They're what happens when one galaxy sits at the bottom of a gravitational well for 10 billion years and eats everything that falls in. Their stellar populations are overwhelmingly old. Their colours are golden yellow or red, reflecting the dominance of ancient metal-rich stars that formed billions of years ago in the galaxies that were consumed. They have very little ongoing star formation because the mergers that built them also heated and expelled the gas needed to make new stars. They are enormous, ancient, slowly dying, and utterly dominant within their clusters. The supermassive black holes at the centers of these galaxies are among the most massive ever discovered. While the Milky Way's central black hole weighs roughly 4 million solar masses and Andromeda's weighs roughly 100 million, the black holes in seedy galaxies can weigh tens of billions of solar masses. These are not merely large. These are objects whose event horizons are wider than our entire solar system. Gravitational engines so powerful that they shape the thermal properties of gas across millions of light years of cluster space. When these black holes were actively feeding, their energy output influenced star formation rates in galaxies hundreds of thousands of light years away from the cluster center. Even now, in their quieter phase, their gravitational influence dominates the dynamics of the cluster core. There is a specific seedy galaxy that has become one of the most famous objects in extragalactic astronomy. It sits at the center of a galaxy cluster called Abell 2029, located over 1 billion light-years from Earth. It was first recorded over 2 centuries ago, at a time when the very concept of an external galaxy did not exist. For more than 100 years, it sat unnoticed in astronomical catalogues, a faint mark waiting for instruments powerful enough to reveal what it truly was. It would take the development of modern astrophysics, space-based telescopes, and deep imaging surveys to reveal what that smudge actually was. And when astronomers finally turned their instruments toward it, with sufficient power and precision, what they found defied the assumptions of even the astronomers who had spent their careers studying galactic structure. A galaxy so large that existing frameworks for categorizing size stopped being useful. A galaxy whose visible stellar body dwarfs the Milky Way and Andromeda combined, whose diffuse halo stretches across millions of light-years, and whose central black hole ranks among the most massive ever measured. A galaxy that became famous precisely because it seemed to represent the upper limit of how large a single galactic body could possibly grow. Its catalogue designation is IC111, and the story of this galaxy is not merely a story of size, it is a story about what happens when the universe takes the process of galactic growth and pushes it to an extreme that makes every familiar reference point begin to feel meaningless. But before we can understand what makes IC 1101 so extraordinary, we need to absorb one more uncomfortable truth about the galaxies we already know. The Milky Way and Andromeda are large by normal standards. They are among the bigger galaxies in the local group and in the local cosmic neighborhood. But compared to the true giants, the seedy galaxies at the centers of massive clusters, they are modest. Consider Messier 87, the supergiant elliptical galaxy at the center of the Virgo cluster. Messier 87 has an estimated diameter of roughly 240,000 light-year, comparable to Andromeda, but packed into an elliptical shape rather than a disk. It contains several trillion stars and hosts a central black hole weighing 6.5 billion solar masses. The same black hole whose shadow was famously imaged by the Event Horizon Telescope in 2019. Messier 87 is enormous. It is one of the most massive galaxies within a few 100 million light-years of Earth, and yet in the hierarchy of seedy galaxies, it is not even close to the top. There are galaxies in more distant and more massive clusters that make Messier 87 look like a stepping stone. Galaxies whose halos stretch not hundreds of thousands of light-years, but millions. Galaxies that have consumed so many others that their stellar populations number in the tens of trillions. Galaxies that sit in clusters so dense and so gravitationally intense that the light from more distant objects behind them is visibly bent and distorted, smeared into arcs and rings by the cluster's gravitational lensing effect. These are not exotic theoretical objects. They are observed, catalogued, and measured. They appear in deep imaging surveys as golden blobs surrounded by halos of diffuse light, so extensive that the boundary between galaxy and cluster becomes a matter of scientific definition rather than physical fact. And among all of them, one has consistently stood out as the most extreme example of visible galactic size. One has been cited again and again in astronomical literature as the galaxy that pushes the concept of the galaxy to its breaking point. One sits in its cluster like a colossus at the centre of a city, surrounded by the debris of everything it has ever consumed. That galaxy is our destination, and reaching it requires not a spaceship, but a willingness to abandon every intuitive sense of how large a single object in the universe can be. Because what we are about to encounter is not just a big galaxy. It is a galaxy so big that the tools we normally use to feel cosmic scale, the comparisons to the Milky Way, the references to Andromeda, the analogies with distances we can barely imagine, all of them begin to buckle under the weight of the numbers. The jump from the Milky Way to Andromeda is significant. The jump from Andromeda to Messier 87 is impressive. But the jump from anything we have discussed so far to IC 1101 is something else entirely. It is the moment where size stops being a number and starts becoming a feeling, a specific kind of unease that arrives when you realize the universe can build structures so far beyond your frame of reference that the frame itself cracks. Everything we've covered so far, every star count, every light-year measurement, every description of the Milky Way and Andromeda, and the local group and galaxy clusters, all of it has been preparation, because none of those numbers matter on their own. They matter because of what they become when you place them next to what comes next. The Milky Way is enormous. Andromeda is larger. Messier 87 is larger still. But the galaxy at the centre of Abel 2029 exists on a scale that reduces all three of those references to minor footnotes. And the most disturbing part is not how big it is. The most disturbing part is what its existence tells us about what the universe is capable of building when gravity has enough time, enough material, and enough patience to work without limit. We are about to meet IC 1101, and once you see what it is, you will never think about the word galaxy the same way again. On the 19th of June 1790, William Herschel pointed his telescope toward a patch of sky near the border of the constellations Virgo and Serpents and recorded a faint smudge of light. He catalogued it, as he did with thousands of other objects during his decades-long survey of the heavens, and moved on. Herschel had no way of understanding what he was looking at. The concept of galaxies as vast external systems of stars separate from our own Milky Way would not be established for another 130 years. To Herschel, the object was simply another nebula, another fuzzy patch among hundreds of fuzzy patches scattered across the sky. He noted its position, its approximate brightness, and nothing more. The smudge disappeared into the records and waited. It waited through the 19th century, through the development of spectroscopy and the first measurements of stellar distances. It waited through the great debate of the 1920s when Edwin Hubble proved that certain nebulae were in fact entire galaxies lying millions of light years beyond the Milky Way. It waited through the construction of ever larger telescopes, through the space age, through the launch of orbiting observatories that would see the universe without atmospheric distortion. And when astronomers finally turned the full power of modern instrumentation toward that faint smudge recorded by Herschel more than 2 centuries earlier, what they found was one of the most extreme single objects in the observable universe. The galaxy carries the designation 1C101. It is the 111th entry in the index catalogue of nebulae and clusters of stars. A supplement to the new general catalogue first published in 1895 by the Danish astronomer John Louis Emil Dreyer. The name is unglamorous, bureaucratic, a filing label rather than a title. But the object it refers to is anything but ordinary. IC 1101 is a supergiant CD galaxy sitting at the exact gravitational centre of a massive galaxy cluster called AEL 2029. It lies approximately 1.15 billion light-year from Earth, which means the light we observe from it today left the galaxy when multicellular life on Earth was still a relatively recent evolutionary development. Everything we know about IC 1101, every measurement, every image, every spectrum describes the galaxy as it existed over 1 billion years ago. What it looks like now, in this moment, we will never know. But what we do know is staggering. The first thing astronomers measure when studying a distant galaxy is its size. And this is where IC 11101 immediately separates itself from everything we have discussed so far. Measuring galaxy size is not straightforward because galaxies do not have hard edges. They fade gradually from bright cores to dim outer regions to halos of diffuse light that eventually blend into the darkness of intergalactic space. Where you draw the line determines the number you get, and different methods produce different answers. For IC 1101, the most commonly used scientific measurements give an isophotral diameter, which is the diameter measured at a specific surface, brightness threshold of approximately 400,000 to 550,000 light-years. The lower estimate comes from measurements taken in visible blue light using the standard method recommended for galaxy cataloguers. The higher estimate comes from infrared observations by the 2-micron all-sky survey, which detects older redder stars that glow more prominently at longer wavelengths. Both numbers are already extraordinary. At 400,000 light-years, IC 1101 is roughly 4 times the diameter of the Milky Way at 550,000 light-years. It approaches 6 times the diameter, but these measurements only describe the galaxy's brighter stellar body. Beyond that body lies something even more remarkable. Deep imaging observations, particularly those conducted in the red light bands, revealed a vast diffuse stellar halo extending outward from the core to a radius of approximately 2 million light-year. That gives a total halo diameter of roughly 4 million light-year. Some sources have cited as diameter as large as 6 million light-year, though this figure is not well supported by primary data and likely includes intra-cluster light. The faint glow of stars that have been stripped from their parent galaxies and now drift freely through the cluster. Gravitationally associated with IC 1101, but arguably belonging to the cluster as a whole rather than to the galaxy itself. This is where the numbers begin to break human intuition. Let me try to make the scale tangible, because abstract comparisons accomplish nothing if you cannot feel them. The Milky Way at its widest reasonable estimate spans about 200,000 light-year. Andromeda spans roughly 220,000 light-year. The distance between the Milky Way and Andromeda is approximately 2.5 million light-year. Now picture the visible stellar body of IC 1101 placed at the center of our local group of galaxies at 400,000 to 550,000 light-year across just the visible body, not the halo would extend well beyond the Milky Way in every direction. Its bright inner region alone would engulf our galaxy entirely. You would not find the Milky Way at the edge of IC 1101, you would find it embedded inside, swallowed a minor structure within a vastly larger one. Now extend the picture to include the halo. At a radius of 2 million light-years, the diffuse stellar envelope of IC 1101 reaches nearly to the distance of Andromeda itself. The halo of a single galaxy would span a significant fraction of the gap between the two largest galaxies in our local group. If IC 1101 were placed at the Milky Way's location, it would not merely dwarf our galaxy, it would engulf Andromeda, the large Melanic Cloud, the small Melanic Cloud, the Triangulum Galaxy, and nearly every other galaxy in the local group. A single galaxy occupying the space that our entire galactic neighbourhood currently fills. Try to feel this in a different way. Imagine you could travel at the speed of light, the absolute fastest anything can move in our universe. Starting at one edge of IC 1101 stellar body and flying toward the other, you would travel for more than 400,000 years before emerging. On the far side, if you began that journey when Neanderthals still walked the Earth alongside early modern humans, you would not have arrived yet, and that only crosses the stellar body. To traverse the full halo from one edge to the other, your journey at light speed would take roughly 4 million years. When you began, the genus Homo had barely appeared on the African savanna. By the time you finished, you would have travelled for the entire span of human evolutionary history and then continued for millions of years beyond it. That is the diameter of a single galaxy's diffuse envelope of light, or consider it from the perspective of the stars themselves. IC 1101 contains approximately 100 trillion stars. If you stood on a hypothetical planet somewhere within the galaxy and looked up, the sky would not resemble anything you know from Earth. In the dense inner regions, stars would crowd the sky in every direction, a blazing canopy of golden yellow light with no dark patches, no constellations, no recognizable patterns. Farther from the core, in the sparse outer halo, the view would thin dramatically. Stars would appear scattered and faint, separated by gulfs of darkness, so wide that neighbouring stars might be invisible to the naked eye. The galaxy would feel different depending on where you stood inside it. Near the centre, overwhelming brightness. Near the edge, a lonely dimness fading into the black void between galaxies. A single object containing environment so varied that its own inhabitants, if any, existed, would disagree about what kind of universe they lived in. Sit with that for a moment. The local group is not a small structure. It contains more than 80 galaxies spread across roughly 10 million light-year of space. Our entire gravitational family of galaxies, everything we can see with the naked eye and everything we cannot, occupies a volume that a single galaxy could substantially fill. IC 1101 does not merely compete with the Milky Way, it competes with the local group. The stellar population of IC 1101 reinforces this disparity. 100 trillion stars compared to the Milky Way's 200 to 400 billion. That is a ratio of roughly 250 to 500 times more stars. 100 times more than Andromeda's trillion. 100 trillion nuclear furnaces, most of them old, most of them slowly cooling, most of them bathing the galaxy in the golden yellow light characteristic of ancient metal-rich stellar populations. These are stars that formed billions of years ago in the dozens or perhaps hundreds of smaller galaxies that IC1 consumed over its long history. Each wave of mergers brought in new stellar populations, which were gravitationally mixed and redistributed throughout the growing body of the central giant. The result is a galaxy whose starlight is not homegrown but inherited. assembled from the contributions of countless smaller galaxies that no longer exist as independent objects. The galaxy's morphological classification tells part of the story of how it grew so large. IC 101 is classified as a seedy galaxy, which places it in the specific category of supergiant galaxies that occupy the centers of rich clusters. Its exact shape has been debated. Some classifications describe it as an elliptical galaxy, a three-dimensional blob of stars with no disk structure and no spiral arms. Others classify it as a lenticular galaxy, a transitional form between spirals and ellipticals that possesses a disk-like structure but lacks spiral arms. The distinction matters less than what both classifications agree on. IC 11101 is not a spiral. It does not have the organized rotating disk of stars and gas that characterizes galaxies like the Milky Way and Andromeda. It's a massive, roughly spheroidal collection of old stars that have been gravitationally scrambled by billions of years of mergers. Whatever spiral structures its progenitor galaxies once possessed were destroyed long ago, torn apart and absorbed into the chaotic orbits of the final merged product. To understand the violence of that construction process, think about what a single galactic merger actually looks like. When two large galaxies collide, the event unfolds over hundreds of millions of years. First, the dark matter halos, invisible but gravitationally dominant, begin to interpenetrate. Then, tidal forces stretch both galaxies into distorted shapes, pulling streams of stars into long tails that can extend millions of light years into intergalactic space. Gas clouds in both galaxies compress, triggering violent bursts of star formation. Supermassive black holes at the centers of both galaxies spiral inward toward each other, dragged by dynamical friction, eventually merging in an event that releases gravitational waves detectable across the universe. The entire process is chaotic, destructive, and creative, simultaneously forging a new and larger galaxy from the wreckage of two smaller ones. Now imagine that process happening not once, not twice, but dozens of times over the course of 10 billion years. Each merger adds mass. Each merger destroys existing structure and replaces it with a larger, more diffuse configuration. Each merger brings in new stars, new gas, new dark matter, and sometimes a new supermassive black hole that must be absorbed by the existing central engine. The galaxy at the bottom of the gravitational well grows relentlessly, fed by everything that spirals inward from the cluster outskirts. It is not growing through peaceful accumulation. It is growing through repeated acts of gravitational violence, each one reshaping the galaxy from the inside out. IC 110-1 is the end product of that violence. It is the scar tissue of a billion years of cosmic collisions smoothed over time into the golden, featureless ball of ancient starlight that telescopes reveal today. This brings us to the heart of the galaxy and to one of its most extreme features. At the center of IC 1101 lies a supermassive black hole whose estimated mass ranks among the highest ever measured. Different methods produce different estimates, but the range spans from roughly 40 billion to 100 billion solar masses using core dynamical models with alternative calculations based on gas, accretion rates suggesting a narrower range of 50 to 70 billion solar masses. To appreciate what these numbers mean, compare them to the supermassive black hole at the center of the Milky Way, Sagittarius, a star, which weighs roughly 4 million solar masses. The black hole in IC 1101 outweighs ours by a factor of 10,000 to 25,000. It is not merely larger, it belongs to a completely different category of gravitational object. Astronomers have described it as overmassive, meaning it is larger than expected even for a galaxy of IC 1101 size, pushing against the theoretical upper limits of how massive a black hole can grow given the constraints of cosmological time and available fuel. A 2017 study using Hubble Space Telescope imaging found that IC1 possesses the largest known galactic core of any galaxy observed to date. The core radius measures approximately 14,000 light-year, which is roughly an order of magnitude larger than the cores of other well-studied giant elliptical galaxies. This oversized core is believed to be the result of a process called core scouring, in which merging supermassive black holes during past galactic collisions gravitationally ejected stars from the central region, carving out a vast depleted zone. The physics of core scouring is both elegant and violent. When two galaxies merge and their central black holes spiral toward each other, the pair forms a gravitationally bound binary system in the merged galaxy's core. As the binary tightens, it interacts with nearby stars through a gravitational mechanism called three-body scattering. Stars that wander close to the binary are flung outward at high velocity, expelled from the core like projectiles from a slingshot. Each ejection removes mass from the central region and transfers energy to the remaining stars, causing them to spread outward over millions of years. This process excavates a cavity in the galaxy's center, creating the diffuse, depleted core that observations reveal. The more mergers a galaxy has experienced, the more black hole binaries have formed and scoured the core, and the larger the resulting cavity becomes. For IC 1101, the mass deficit in the core, the amount of stellar mass that has been ejected by this process has been estimated at roughly 490 billion solar masses. To grasp what that means, consider that 490 billion solar masses is larger than the total stellar mass of most galaxies in the observable universe. The Milky Way's total stellar mass is estimated at roughly 50 to 60 billion solar masses. IC 1101's core deficit alone exceeds the entire stellar content of our galaxy by a factor of 8 to 10. The galaxy has thrown away more stars from its center than the Milky Way contains in total. These ejected stars did not vanish. They were scattered into the outer halo and into the surrounding cluster, contributing to the diffuse envelope of light that extends millions of light-years from the core. The halo of IC 1101 is partly built from the debris of its own internal violence. Stars exiled from the center by the gravitational tantrums of merging black holes. IC 1101 is not forming new stars in any significant quantity. It is in the terminology astronomers sometimes use a dead or dying galaxy. The mergers that built it also heated and expelled the gas needed for star formation. The galaxy accretes roughly 450 solar masses of material per year from the surrounding cluster environment. But this is a slow trickle compared to the vigorous star formation seen in younger gas galaxies. There are no glowing nebulae, no stellar nurseries, no blue supergiant stars blazing with the light of recent creation. IC 1101 glows with the steady fading light of ancient stars, a cosmic monument to a violent past that has now grown quiet. If galaxies had seasons, IC 1101 would be deep in its autumn, with winter approaching slowly over the next billions of years as its oldest stars exhaust their nuclear fuel and wink out one by one. The galaxy's environment reinforces its dominance. Able 2029 is one of the densest galaxy clusters in the sky, containing thousands of galaxies, including hundreds of giant galaxies. Yet, IC 1101 alone accounts for roughly a quarter of the entire cluster's visible light output, a single galaxy producing 1/4 of the luminosity of a structure containing thousands of galaxies. The cluster itself is enveloped in an enormous cloud of superheated gas that glows in X-ray wavelengths, reaching temperatures of roughly 100 million degrees. This gas is held in place by the combined gravitational pull of the cluster's dark matter, and it exerts pressure on the galaxies embedded within. IC 1101 sits at the very centre of this hot gas cloud at the deepest point of the cluster's gravitational potential. Well, exactly where physics predicts the most massive galaxy should reside. The alignment of IC 1101's major axis with the axis along which AEL 2029 accretes, material from a neighbouring cluster called Abell 2033 is not coincidental. It reveals that the galaxy's growth is shaped by the same large-scale gravitational flows that govern the cluster's evolution. Material falls into the cluster along filaments of the cosmic web, channeled by dark matter into streams that feed the central galaxy. IC1 is not just sitting at the centre of its cluster. It is connected to the cosmic web itself, drawing sustenance from the largest structures in the universe. The history of how IC 1101 reached this size is written in the properties of its halo. The smoothness of the stellar envelope suggests that most of the major mergers occurred early in the cluster's history when the universe was younger, and galaxy interactions were more frequent. Studies of brightest cluster galaxies in general suggest that these objects assembled roughly half of their mass through mergers that occurred more than 8 billion years ago, with subsequent growth proceeding more slowly as the rate of galactic infall decreased. IC 1101 likely consumed dozens of major galaxies and hundreds of smaller ones over its lifetime, each collision adding to its mass, expanding its halo, and feeding its central black hole. Think about what that means in concrete terms. Every major galaxy that fell into the centre of Abell 2029 over the past 10 billion years was absorbed into IC 1101. Galaxies that may have been comparable in size to the Milky Way. Galaxies that may have contained their own planetary systems, their own complex chemistry, perhaps even their own biological evolution. All of them consumed, all of their stars now orbiting within the body of a single vast, slowly fading giant. The galaxy is not just large, it is a graveyard, a monument built from the corpses of everything that wandered too close to the centre of the cluster over cosmic time. And this is where the story connects to something uncomfortably close to home. Earlier, we described how the Milky Way and Andromeda are falling toward each other and will merge in roughly 4 to 5 billion years. That merger will destroy both spiral galaxies and create a single massive elliptical galaxy, Milky, containing the combined stellar populations of both. Milky will be large by current standards, perhaps over 1 trillion stars, a respectable elliptical galaxy with a substantial dark matter halo and a merged supermassive black hole formed from the coalescence of the Milky Way's and Andromeda's central black hole engines. It will be the dominant galaxy in whatever remains of the local group. And for a moment, standing in the wreckage of 2 destroyed spirals, it might feel like the end of the story, the final form of our galactic home. But IC 1101 reveals that Milky would not be the end of anything. It would be the beginning, because IC 1101 was built from exactly this kind of merger, repeated over and over across billions of years. Every galaxy that fell into the centre of Abell 2029 was at some point the product of its own previous mergers. Spiral galaxies collided with other spirals to form ellipticals. Ellipticals consumed dwarves. The resulting objects fell deeper into the cluster potential well and were absorbed by the growing central giant. The process is hierarchical recursive and relentless. If the Milky Way and Andromeda happen to sit at the centre of a massive galaxy cluster instead of in the relatively sparse local group, their merger product would not be a final form. It would be an appetizer, a single course in a meal that lasts for 10 billion years and ends with something the size of IC 1101. Milka, the galaxy that will one day contain every star and planet we have ever known, would be a minor meal for IC 1101. It would add barely 1% to the giant's total mass. Its trillion stars would be absorbed, scattered and forgotten in the vast golden halo within a few 100 million years. Nothing about Milomea, not its structure, not its history, not the civilizations that might still exist within it, would survive as a recognizable feature, the product of the Milky Way's and Andromeda's cosmic collision. The thing that inherits everything we are would vanish into the body of the larger galaxy like a raindrop falling into a lake. This is what IC 1101 does. This is what it has been doing for 10 billion years, and the only reason it will not do it to us is that we happen to live in the wrong neighbourhood, too far from any cluster centre to be consumed, too isolated to fall into a gravitational well that would feed us to a waiting giant. Now, here is where the framing of this story becomes important. Because the way IC1 has been described in popular media over the past 2 decades has not always been scientifically precise. You'll find sources claiming that IC 1101 has a diameter of 6 million light-year, making it the largest galaxy in the universe by wide margin. This figure appears on dozens of websites, in popular science articles and in YouTube videos. But if you trace it back to primary scientific literature, it becomes difficult to find a well-sourced origin. The 6 million light-year number likely comes from including the most extended, faintest reaches of the galaxy's halo and possibly conflating it with intracluster light. The faint glow of stars that have been stripped from their parent galaxies and now drift freely through the cluster, gravitationally associated with IC 1101 but arguably belonging to the cluster as a whole rather than to the galaxy itself. This is where the boundary problem of CD galaxies becomes scientifically real. The intracluster light surrounding IC 1101 does not have a clear edge. It fades gradually into the cluster background. Some of those stars are gravitationally bound to IC 1101 and will remain part of it for the rest of cosmic time. Others are free-flying, belonging to the cluster rather than to any individual galaxy, orbiting through the shared gravitational field like orphans in a city that has grown too large to keep track of its inhabitants. Determining which stars belong to the galaxy and which belong to the cluster requires careful dynamical modelling, and different assumptions produce different answers. The galaxy's size is not uncertain because astronomers have been sloppy. It is uncertain because the galaxy itself does not have a clean physical boundary. It blurs into its surroundings in a way that makes the question, where does the galaxy end, genuinely difficult to answer. What is not uncertain is the galaxy's position at the extreme end of the size distribution for visible galaxies. Even at the lower estimate, IC 1101 is among the largest stellar bodies ever observed. Its halo is among the most extensive ever measured. Its core is the largest ever detected. Its black hole is among the most massive ever estimated. By virtually every metric used to evaluate galactic size, IC 1101 sits at or near the top of the distribution. It is the single most commonly cited example of an extremely large visible galaxy, and it has held that status for decades. But the word visible in the previous sentence is doing critical work, and it is the word that opens the door to the next chapter of this story, because IC 1101 is enormous by any standard applied to the stellar body of a galaxy. Its stars, its core, its halo, its black hole, all of them push the boundaries of what astronomers have observed in visible and infrared light. But the universe does not restrict galactic structures to what human eyes or optical telescopes can see. There are galaxies in the cosmos whose influence extends far beyond their stellar bodies, far beyond their halos, far beyond anything that emits light in the wavelengths we associate with stars and gas. And when you measure those galaxies not by their visible extent but by the full reach of their astrophysical structures, the idea of IC 1101 as the undisputed largest galaxy becomes considerably more complicated. This complication is not a weakness in the A story. It does not diminish IC 1101. If anything, it makes the story more unsettling because what it reveals is that the concept of the largest galaxy is not a simple clean record like the tallest building or the longest river. It depends on what you mean by galaxy. It depends on what you choose to measure. And when you start measuring structures that extend beyond the visible stellar body, the scale of what the universe can produce becomes so extreme that even I see one as incomprehensibly vast as it is, begins to look like merely the starting point of a much deeper and more disturbing revelation. There are objects in the cosmos whose galactic structures, measured from end to end, span not millions but tens of millions of light years. Objects whose physical extent dwarfs 1 C1101 by factors of 4 or 5 or even 6. Objects that stretch across distances comparable to the gaps between cosmic web filaments, bridging voids that were supposed to be empty, reaching scales that begin to blur the line between a single galaxy's influence and the architecture of the universe itself. These objects do not achieve their size through stars. They achieve it through something else entirely. Through jets of relativistic plasma fired from the poles of supermassive black holes at nearly the speed of light, inflating enormous loads of radio-emitting gas that extend far beyond anything the galaxy's stars could ever reach. They are called giant radio galaxies, and they represent a completely different way of thinking about what a galaxy can be and how far its influence can extend. IC 1101 earned its reputation as the most extreme visible galaxy for good reason. Its stellar body, its halo, its black hole, its core, all of them push the limits of observed galactic structure. But the universe, it turns out, does not care about categories. It does not separate visible size from radio size into neat, mutually exclusive boxes. It simply builds structures, and some of those structures happen to span distances so vast that the visible galaxy at their centre becomes a footnote in a much larger story. The question of what the largest galaxy really is, the one this entire discussion has been building toward, is about to become significantly stranger, and the answer will not settle the question, it will shatter it. There is a type of galaxy in the universe that most people have never heard of, and it is about to dismantle everything we have so carefully constructed. Because so far, we have been measuring galaxies the way most people instinctively understand, them by their stars, by the visible light they emit, by the extent of their luminous stellar bodies and the diffuse halos that surround them. This is the natural way to think about galaxy size. Stars are what we see when we look at galaxies. Stars are what populate the spiral arms, the central bulges, the elliptical blobs captured in Hubble images. When someone asks how big a galaxy is, the answer almost always refers to the spatial extent of its stars, because stars are what make a galaxy visible in the first place. But the universe has never been particularly interested in limiting itself to what is visible. In the mid-nth century, As radio astronomy matured and telescopes capable of detecting electromagnetic radiation far below the frequency of visible light came online, astronomers began discovering structures associated with galaxies that had no counterpart in optical observations. They found enormous lows of radio-emitting plasma extending outward from certain galaxies, sometimes symmetrically, sometimes slightly offset, stretching into intergalactic space far beyond the visible boundary of the galaxy's stars. These lows were not made of stars. They were not gas clouds in the conventional sense. They were vast reservoirs of magnetized plasma, inflated by relativistic jets of material fired from the vicinity of the galaxy's central supermassive black hole, heated to such extreme energies that they emitted synchrotron radiation detectable by radio telescopes. The mechanism behind these structures deserves a closer look because it is one of the most violent and physically extreme processes in the entire cosmos. At the center of certain galaxies, the supermassive black hole is actively accreting material, pulling in a gas and dust from its surroundings and forming a rapidly spinning accretion disk. This disk is not a calm, orderly structure. It is a superheated maelstrom of plasma spiraling inward at velocities approaching the speed of light, compressed by gravitational forces so intense that the inner regions of the disk and its surrounding corona reach temperatures of hundreds of millions of degrees. Friction within the disk converts gravitational potential energy into radiation, and at the peak of its activity, the accretion disk around a supermassive black hole can outshine the entire galaxy that hosts it. But not all of the infalling material reaches the black hole's event horizon. A fraction of it, channeled by powerful magnetic fields threading the accretion disk and the spinning black hole's aerosphere, gets launched outward along the black hole's rotational axis in two tightly columnated beams called relativistic jets. These jets travel at velocities approaching the speed of light, sometimes exceeding 99% of it. They are among the most energetic phenomena in the universe, carrying the power output of trillions of suns in two narrow beams that punch through the galaxy's interstellar medium and continue outward into intergalactic space. As the jets interact with the surrounding gas, they slow down, spread out, and inflate enormous lows of magnetized plasma. These lows grow over millions of years, fed continuously by the jets, expanding outward until the pressure of the intergalactic medium balances the energy being pumped into them. The electrons in the lobes spiral around the magnetic field lines at relativistic speeds, emitting synchrotron radiation that peaks at radio wavelengths. This radiation is how astronomers detect the lows, which are otherwise invisible to optical telescopes. The lows glow only in radio light, ghostly structures spanning distances that dwarf the visible galaxy. At their center, most radio galaxies produce lobes that extend a few hundred 000 light-year from the central galaxy. Impressive, but comparable in scale to the galaxy's own stellar body. The lows sit like two bubbles flanking the galaxy, visible only in radio wavelengths invisible to optical telescopes. Even the Milky Way has its own pair of modest radio lobes detected in recent years extending above and below the galactic plane. These structures are a normal part of galactic astrophysics, a consequence of black hole activity that most large galaxies experience at some point in their evolution. But there is a subclass of radio galaxies that defies this modest scaling. Astronomers call them giant radio galaxies, and their defining characteristic is that their radio lobes extend to truly extraordinary distances, reaching lengths measured not in hundreds of thousands of light-year, but in millions. Some span several megaparsecs, a unit of distance equal to roughly 3.26 million light-year. These are structures so vast that they do not merely extend beyond their host galaxy. They extend beyond the galaxy's local environment, beyond the scale of galaxy groups, into the spaces between cosmic web filaments. They are by some metrics the largest coherent structures produced by a single galactic source in the observable universe. Giant radio galaxies have been known for decades. By the early 2020s, hundreds of them had been catalogued. Most discovered through radio surveys that mapped the sky at low frequencies where these extended diffuse structures are easiest to detect. But the discoveries that shattered the public conversation about the largest galaxy came in rapid succession, starting in 2022, and they changed the framing of this question permanently. In February of 2022, a team of astronomers led by Martijn Owe at the Leiden Observatory in the Netherlands published a paper announcing the discovery of a giant radio galaxy they named Alcyoneus after one of the giants of Greek mythology. The galaxy was identified in data from the Low Frequency Array, or LOR, a network of roughly 20,000 individual radio antennas distributed across 52 stations in Europe. LOR operates at frequencies far below what optical telescopes detect, and its sensitivity to faint diffuse radio emission makes it ideally suited for detecting the extended lows of giant radio galaxies. What Owe and his colleagues found was remarkable. Alcyon possessed a radio structure spanning approximately 5 megaparsecs in projected length, which translates to roughly 16 million light-year from one lobe edge to the other. To put that in context, the Milky Way is approximately 100,000 to 200,000 light-years across. Alcyoneus's radio structure was roughly 100 times the diameter of the Milky Way, laid end to end. You would need 100 Milky Way galaxies to match the span of this single radio structure. At the time of its discovery, it was the largest known structure of galactic origin ever detected. The media response was immediate and in many cases misleading. Headlines declared Alcyoneus the largest galaxy in the universe. Social media amplified the claim. The name Alcyoneus began appearing on lists of cosmic records alongside IC 1101, often presented as though the two objects were competing in the same category. But this framing obscured a critical distinction that matters enormously for understanding what largest actually means. Alcyoneus's host galaxy, the actual stellar body at the center of the radio structure, is not exceptional. Its stellar mass is estimated at roughly 240 billion solar masses, which is only a few times that of the Milky Way and far smaller than I. See, 1101's estimated 100 trillion stars. Its central supermassive black hole weighs approximately 390 million solar masses, a respectable but entirely ordinary mass for an elliptical galaxy, and roughly 100 to 250 times less massive than the black hole in IC1. The galaxy itself does not host a quasar. Its star formation rate is negligible at roughly 1/160th of a solar mass per year. By every measure of the visible stellar body, the host galaxy of Alcyoneus is unremarkable. It is an ordinary elliptical galaxy, embedded in a filament of the cosmic web, indistinguishable from thousands of similar objects scattered throughout the observable universe. What makes Alcyon extraordinary is not its galaxy. It is its jets. It is the two enormous lows of magnetized plasma extending millions of light-years in opposite directions from the central black hole, inflated over millions of years by relativistic outflows that have been pumping energy into intergalactic space. These lows are not made of stars. They contain no planets, no solid matter, no structure that would be recognizable as galactic in the traditional sense. They are tenuous, diffuse clouds of plasma so thin that their internal pressures rank among the lowest, ever measured in any astrophysical structure approximately 5 asterisk, 10 circumflex, the 16th pascals. They glow only in radio wavelengths invisible to any optical telescope ever built, and this is the detail that makes Alcyon so conceptually disorienting. The galaxy at the centre is ordinary, unremarkable, a galaxy you walk past in a catalogue without a second glance. Its stellar mass is half that of the Milky Way. Its black hole is 100 times less massive than the largest known. Its radioluminosity sits at roughly the 45th percentile of all known giant radio galaxies, meaning more than half of them are actually brighter. The mismatch between cause and effect is almost absurd. Strip away the radio lobes and you are left with a galaxy that no survey would flag as unusual. Restore them and you are looking at a structure 100 times wider than the Milky Way. The engine is modest. The output is colossal. It is as if a garden hose somehow produced a river. This disconnect between the host galaxy and the scale of the radio structure is one of the deepest puzzles in modern extragalactic astronomy. If the jets were driven by an exceptionally powerful black hole, the enormous size would make intuitive sense. More power, more reach. But Alcyoneus has a modest black hole by the standards of active galaxies. If the jets were unusually energetic, that would explain the extent. But Alcyoneus's jet luminosity is ordinary, the most plausible explanation, and the one proposed by the Discovery team, is that the growth of the radio lobes was primarily determined not by the power of the central engine, but by the density of the surrounding environment. Alcyoneus resides in a filament of the cosmic web, where the intergalactic medium may be less dense than average, with less resistance pushing back against the expanding lobes. The same modest jet power that would produce ordinary-sized lows in a denser environment instead produced a structure spanning 16 million light-year in the relative vacuum of a sparse cosmic filament. This is the core of the ambiguity. When the media called Alcyoneus the largest galaxy, they were including the radial lobes in the measurement, but radio lobes are not typically considered part of a galaxy's size in standard astronomical usage. They are ejecta material expelled from the galaxy rather than material contained within it. The Wikipedia article on Alcyoneus itself notes that various media outlets described it as the largest galaxy known, but adds that this is misleading because radio ejecta are not often taken into consideration in determining galaxy sizes. The distinction is not pedantic. It reflects a genuine scientific question about what a galaxy is. Is a galaxy defined by its stars? By the gravitational extent of its dark matter halo? By the furthest reach of any structure physically connected to its central engine? The answer determines whether Alcyoneus is the largest galaxy ever found, or merely the galaxy with the largest radio ejecta ever found. And those are meaningfully different claims. But even as astronomers were processing the implications of Alcyoneus, the record was already being broken again. In September of 2024, a paper published in the journal Nature by a team again led by Martine announced the discovery of an even larger giant radio galaxy. This one was named Porphyrion, after another giant of Greek mythology, and its scale made Alcyoneus look modest by comparison. Porphyrion's radio jets span approximately 7 megaparecs, or roughly 23 million light-year from end to end. That is 140 times the diameter of the Milky Way. If you could somehow see Porphyrion's full extent with the naked eye, the two lows would dominate a colossal swath of the sky, dwarfing any individual galaxy by an almost absurd margin. The host galaxy lies 7.5 billion light-year from Earth, meaning the jets existed when the universe was only 6.3 billion years old, less than half its current age. Despite its extreme youth in cosmic terms, the central black hole generated jets with a combined power output equivalent to the energy of trillions of suns, punching plasma into intergalactic space at nearly the speed of light and inflating lows that stretched across a volume of space, comparable in scale to the gaps between filaments of the cosmic web. Porphyrion's discovery carried implications that went far beyond the question of galactic size records. The research team calculated that the jets span roughly 2/3 the radius of a typical cosmic void at the epoch of universal history. This means a single galaxy's outflows were reaching scales that interact not just with the galaxy's local environment, but with the large-scale structure of the universe itself. The jets were threading through the cosmic web, potentially magnetizing the intergalactic medium, heating the gas between filaments, and influencing the formation and evolution of other galaxies located millions of light-years from the source. Aoi and his colleagues wrote that their findings suggest every place in the universe may have been affected by black hole activity at some point in cosmic time. This idea that black hole jets might be responsible for magnetizing the cosmos on the larger scales represents a significant shift in astrophysical thinking. For years, the origin of magnetic fields in the intergalactic medium was a nagging puzzle. Observations confirmed that the gas between galaxies is permeated by weak but measurable magnetic fields, but the mechanism that produced them was debated. One leading hypothesis, called the Biermann battery effect, proposed that magnetic fields arise naturally from the differential motion of electrons and ions under gravitational forces. This mechanism works, but it produces extremely weak seed fields that need amplification by other processes to match observed strengths. Giant radio galaxy jets offer an alternative and potentially more powerful explanation. If jets spanning tens of millions of light-years routinely inject magnetized plasma into the intergalactic medium, they could be the primary source of cosmic magnetism on the larger scales. Porphyrion's discovery strengthened this hypothesis by demonstrating that jet structures can reach sizes comparable to the cosmic web itself, placing magnetized plasma exactly where it would need to be to explain the observed intergalactic fields. And even Porphyrion's record did not last. By late 2024, another radio galaxy designated TXS 00033 plus 252 was identified with an estimated radio structure spanning approximately 8 megapex, or roughly 26 million light-years. The records are falling faster than the community can absorb them, driven by the unprecedented sensitivity of law and the growing recognition that giant radio galaxies are far more common than previously believed. A citizen science effort associated with the law surveys has already identified more than 10,000 jet pairs spanning roughly 3 million light-year or more. These are not rare curiosities. They are a population, a class of objects that the universe produces, routinely, and their typical scales dwarf anything measured in visible starlight. Now, pause and consider what this means for the question at the heart of this discussion. What is the largest galaxy we have ever found? The answer depends entirely on how you define galaxy. If you define a galaxy by its visible stellar body, the extent of its stars and the light they produce, then IC 1101 remains one of the strongest candidates. Its isopodal diameter of 400,000 to 550,000 light-year, combined with a diffuse stellar halo extending to roughly 4 million light-year, places it at or near the top of every observed distribution of visible galactic size. No other galaxy has been reliably measured with a brighter, more extended stellar body. In the category of visible galactic size, IC 1101 is the anchor, the reference point, the object that defines the extreme end of the scale. But if you define a galaxy by the total extent of any coherent physical structure connected to its central engine, including radio lobes inflated by relativistic jets, then the record belongs to objects like Porphyrion and its successors. Their physical extents of 23 to 26 million light-year exceed the halo of IC 1101 by factors of roughly 6 to 7. They reach distances that place them in a different category entirely. Structures that span not just galactic scales, but cosmological ones. The tension between these two definitions is not a flaw in astronomy. It is a reflection of a genuine physical reality. Galaxies are not simple objects. They are multi-layered systems with stellar bodies, dark matter halos, gas reservoirs, magnetic fields, and in some cases, relativistic outflows that extend far beyond anything the stars alone could reach. Choosing where to draw the boundary is not arbitrary, but it is a decision, and different decisions produce different answers. An astronomer studying stellar populations might define galaxy size by the extent of the stars and conclude that IC 1101 is the largest. A radio astronomer studying jet physics might define galaxy size by the extent of the radio structure and conclude that Porphyrion holds the record. Both are correct within their frameworks. Neither is wrong. The universe simply does not provide a single unambiguous answer. But here is what matters more than the record itself. The existence of these giant radio structures tells us something deeply uncomfortable about the range of scales the universe can produce from a single galactic source. When Alcyoneus was discovered, astronomers were surprised not by the existence of giant radio galaxies which had been known for decades, but by the fact that the host galaxy was so ordinary. Its stellar mass was average, its black hole was average, its jet luminosity was average. Nothing about the central engine was exceptional, yet it produced a radio structure spanning 16 million light-years. The implication was that giant radio galaxy growth might not require unusual central engines. It might require only the right environment, a low-density region of the cosmic web where the intergalactic medium offers minimal resistance to the expanding lows, allowing them to grow to extraordinary sizes without being confined by external pressure. Porphyrion complicated this picture further because its host galaxy is more massive. Roughly 10 times the mass of the Milky Way, and its black hole operates in a different mode, a radiative mode rather than the jet mode typical of most giant radio galaxies. This was unexpected because radiative mode black holes were not previously known to produce jets of this scale. The discovery implied that the conditions for giant jet growth might be more varied and more common than astronomers had assumed. If both ordinary and massive host galaxies can produce jets spanning tens of millions of light-years, and if the primary limiting factor is the density of the surrounding intergalactic medium rather than the power of the central engine, then the universe may contain far more of these structures than current surveys have detected. Lore has so far surveyed only about 15% of the sky. The population of giant radio galaxies identified already numbers in the thousands, and the survey is nowhere near complete. Aoi himself has stated that astronomers may be looking at the tip of the iceberg. The true population of structures spanning millions of light-years could be vastly larger than current catalogues suggest. This realization does not diminish IC 1101. If anything, it contextualizes it more precisely. IC 1101 represents the extreme of one kind of galactic scale, the visible stellar kind, its stellar body, its halo, its core, its black hole. all push the limits of what the universe can build through gravitational assembly and galactic mergers. It is the end product of billions of years of gravitational assembly at the center of a massive galaxy cluster. And in terms of the sheer mass and extent of assembled starlight, it remains one of the most extreme objects ever observed. But the giant radio galaxies represent the extreme of a different kind of galactic scale, the kind measured not in stars but in energy and magnetic fields, in the reach of relativistic plasma driven outward by the most powerful engines in the cosmos. These structures do not compete with IC 11101 for the same title. They occupy a different axis of extremity entirely. And the fact that both kinds of extreme exist, that the universe can build galaxies as visually massive as IC 11101 and simultaneously produce single-source structures as physically extended as Porphyrion, is what makes this story genuinely unsettling rather than merely impressive. Because the real question is not which galaxy holds the record. The real question is what it means that the universe can produce structures at these scales at all. A galaxy whose stars span 500,000 light-year and whose halo reaches 4 million. A single black hole's outflow that spans 23 million light-year. A population of giant jets numbering in the tens of thousands. Most of them still undetected. The scales involved are not just large. They are large enough to interact with the cosmic web itself, the largest organizational structure in the universe. When a single galaxy's jets can stretch across 2/3 the radius of a cosmic void, the old image of a galaxy as an island surrounded by empty space stops working. These objects are not contained by their local environment. Their outputs leak across distances that compete with the spacing of the cosmic web's own filaments, depositing magnetized plasma into regions no star from the host galaxy will ever reach. A single galactic engine is operating on a canvas that was supposed to belong to the universe alone. This is where the emotional weight of the story shifts. We began by establishing that a single ordinary galaxy is already incomprehensibly large. Then we showed that IC 1101 pushes visible galactic size to a point where familiar references like the Milky Way and Andromeda stop functioning as meaningful comparisons. Now we have seen that the concept of the largest galaxy itself resists clean definition, because the universe produces galactic structures across multiple axes of scale that do not collapse into a single ranking, and the structures at the top of each axis are so extreme that they begin to blur the categories astronomers use to organize the cosmos. A galaxy is supposed to be a bounded object, a collection of stars and gas and dark matter held together by gravity, distinct from its surroundings, definable, measurable. But when a galaxy's radio lobes extend 23 million light-year into intergalactic space, is the structure still a galaxy when a galaxy's stellar halo merges imperceptibly into the intracluster, light of its parent cluster? Where does the galaxy end and the cluster begin? When a galaxy's jets magnetize the cosmic web across scales rivaling the distances between filaments, is the galaxy's influence truly local? These are not rhetorical questions, they are active areas of research, and the answers, when they come, will likely reveal that the boundaries we draw around galaxies are human constructs imposed on a cosmos that does not recognize them. The universe builds structures continuously from stellar scales to galactic scales to cluster scales to cosmic web scales. And the transitions between them are not sharp. They are gradients, zones of diminishing influence that fade rather than end. A galaxy is not a thing with an edge. It is a concentration of matter and energy at the center of a zone of influence that extends in principle forever. IC 1101 and Porphyrion are both expressions of this truth. One represents the extreme of gravitational assembly, the largest visible pile of stars ever observed. The other represents the extreme of energetic outflow, the farthest reach of a single black hole's relativistic jets. Both are galaxies. Both defy simple measurement. Both force us to confront the uncomfortable reality that the universe's capacity for building large structures has no obvious ceiling. And it is that absence of a ceiling, that sense of unlimited upward scale, that transforms this story from a record book into something more deeply troubling. Because if the largest visible galaxy can span 4 million light-year, and the longest radio jets can reach 26 million, and the population of giant structures numbers in the tens of thousands, with most still undetected, then we are not looking at outliers. We are looking at the edge of a distribution whose full extent we have not yet mapped. Somewhere in the unobserved sky, there may be structures even larger, structures that have not yet been detected, because our surveys are incomplete, because our instruments lack the sensitivity, because the universe has had billions of years to build things we've not yet imagined. The largest galaxy we've ever found may not be the largest galaxy that exists. And that possibility is where the final layer of this story begins. Let us go back to the beginning. Not the beginning of this story, but the beginning of the intuition we've been slowly dismantling across everything that came before. The intuition that says a galaxy is a knowable thing, a structure with a shape, a size, a boundary, something you could point to on a chart and say that is a galaxy. It starts here, it ends there, and everything outside it is something else. That intuition feels natural because it is how we experience every other object in our lives. A mountain has a base and a peak. An ocean has a shore. A city has a boundary where the buildings stop and the countryside starts. We are wired to think in terms of objects, edges, categories, and for most of human history, that wiring served us well. But the universe at the scales we've been exploring does not operate the way our wiring expects, and the story of the largest galaxy ever found is ultimately the story of what happens when the wiring encounters something it was never designed to process. Start with the Milky Way. 100,000 to 200,000 light-year across, 200 to 400 billion stars, a supermassive black hole weighing 4 million solar masses, a barred spiral structure with arms of gas and dust and young stars wrapping around a central bulge of older, redder stellar populations. This is home. This is the galaxy that contains every star you have ever seen, every planet humanity has ever studied, every signal we have ever sent into the void. It is so large that light requires 100,000 years to cross it. It is so massive that its gravitational influence shapes the orbits of more than 80 satellite galaxies. It contains more worlds than any human civilization could explore in 1,000,000 lifetimes. And yet, in the context of this story, the Milky Way has served only as a starting point, a baseline, the first rung on a ladder that climbs so far upward that the bottom rung eventually disappears from view. Andromeda came next, roughly 220,000 lighter years across, 1 trillion stars, a black hole weighing 100 million solar masses, larger than the Milky Way by every meaningful metric. If the Milky Way is an average house on a residential street, Andromeda is the mansion at the end of the block. Impressive. Dominant. The biggest thing in the immediate neighborhood, and the two of them are falling toward each other at 250,000. Locked in a gravitational embrace that will end in a collision roughly 4 to 5 billion years from now. When that collision occurs, Both galaxies will be destroyed as independent structures and reformed into a single massive elliptical galaxy containing the combined stellar populations of both. That merged galaxy will be among the largest structures in the local cosmic neighborhood, and it will still be smaller than IC 1101 by a factor that renders the comparison almost meaningless. IC 1101, a supergiant CD galaxy at the center of the Abell 20029 galaxy cluster, 1.15 billion light-year from Earth, an isopotal diameter of 400,000 to 550,000 light-year for the visible stellar body, a diffuse stellar halo extending to a radius of roughly 2 million light-years, giving a total extent of approximately 4 million light-year, 100 trillion stars, a supermassive black hole weighing between 40 and 100 billion solar masses, the largest known galactic core ever measured, spanning roughly 14,000 light-years, carved out by the mergers of supermassive black holes during billions of years of relentless galactic consumption, a galaxy whose halo alone could swallow the distance between us and Andromeda, a single structure vast enough to replace our entire local group and still have room at the margins. That is the visible giant. That is the galaxy that held the popular title of largest in the universe for decades. And that still stands as one of the most extreme examples of assembled starlight ever observed. And for a long time that was where the story ended. The biggest galaxy was IC 1101. The number was 4 to 6 million light-years depending on how you measured the halo. And the emotional conclusion was straightforward, or a galaxy bigger than our local group. Case closed. But the story did not end there. It could not, because the universe was not finished revealing what it had built. Alcyoneus discovered 2022, a giant radio galaxy whose relativistic jets inflate lobes of magnetized plasma spanning approximately 16 million light-year, roughly 100 times the diameter of the Milky Way. The host galaxy is ordinary. Its stellar mass is only modestly above the Milky Way's. Its black hole is modest by the standards of active galaxies. Nothing about the central engine is exceptional. And yet the structure it produced is 4 times larger than the full halo extent of IC 1101. Porphyrion reported 2024. Jets spanning approximately 23 million light-year, 140 times the diameter of the Milky Way. A structure so large that it stretches across roughly 2/3 the radius of a cosmic void at the epoch when it existed, reaching scales that interact with the cosmic web itself. The host galaxy is 10 times the mass of the Milky Way. Substantial, but not extraordinary. The jets date to a time when the universe was only 6.3 billion years old, less than half its present age. A single black hole less than halfway through cosmic history, producing an outflow that bridges the gap between the local galactic environment and the large-scale structure of the universe. And then TXS 0033 plus 252 identified in late 2024. Radio structure spanning approximately 26 million light-years, surpassing Porphyrion. Another record broken before the previous one had been fully absorbed by the scientific community. Another demonstration that the upper limit of galactic structural extent has not yet been found. Now lay these out in sequence and feel the ladder. The Milky Way 100,000 to 200,000 light-years. Andromeda 220,000 light-years. IC 1101 stellar body 400,000 to 550,000 light-year. IC 1101 full halo, approximately 4 million light-year. Alcyoneus full radio structure, approximately 16 million light-years. Porphyrion full radio structure approximately 23 million light-years. TXS 0033 plus 252 approximately 26 million light-year. Each step on that ladder does not merely increase the number, it changes the category. The jump from the Milky Way to Andromeda is a jump within the same class of objects, spiral galaxies of roughly similar structure. The jump from Andromeda to IC 1101 is a jump from a large spiral to a supergiant elliptical, a fundamentally different type of galaxy built through fundamentally different processes. The jump from IC 1101's stellar body to its halo is a jump from the galaxy's bright interior to its fading gravitational periphery, a zone where the boundary between galaxy and cluster becomes ambiguous. And the jump from IC 1101's halo to the radio structures of Alcyoneus and Porphyrion is a jump from assembled starlight to relativistic plasma, from gravitational architecture to energetic outflow, from the galaxy as a collection of stars to the galaxy as a source of influence that extends across cosmological distances. At each step, the previous reference point shrinks. The Milky Way, which felt impossibly vast at the start, becomes a rounding error by the time you reach IC 1101. IC 1101, which seemed like the ultimate expression of galactic scale, becomes a dot at the center of Porphyrion's radio structure. The comparisons that once made you feel the size, the ones that said IC 1101 could swallow the local group, or that Porphyrion equals 140 Milky Ways laid end to end, stop producing the emotional response they were designed to create. The numbers are too large. The gaps between the rungs are too wide. The ladder has climbed past the altitude where human intuition can breathe. This is what I mean when I say scale itself fails. It is not that the numbers become meaningless in a mathematical sense. They remain precise, measurable, scientifically valid. It is that they become meaningless in a human sense. The emotional apparatus we use to process size. The instinct that makes a mountain feel large and a continent feel larger breaks down when confronted with structures that span millions or tens of millions of light years. We lose the ability to feel the difference between 16 million light years and 23 million light years, because both numbers are already so far beyond anything we can viscerally imagine that adding 7 million more makes no experiential difference. The ladder keeps climbing, but at some point the climber goes numb, and that numbness is itself the point, because the terrifying truth about the largest galaxy we've ever found is not a specific number. It is not 4 million light-years, or 16 million, or 23 million. The terrifying truth is the shape of the distribution. It is the fact that every time astronomers survey a new patch of sky with better instruments, they find structures larger than the ones they knew about before. It is the fact that Law has surveyed only 15% of the sky and has already identified more than 10,000 giant jet pairs spanning millions of light years. It is the fact that the records keep falling, not because we're getting close to the maximum, but because we keep discovering that the maximum is further away than we thought. There is no indication that we've found the largest galactic structure the universe has produced. There is no theoretical ceiling that says radio jets cannot extend beyond 30 million light-year or 40 or 50. The limiting factor appears to be the density of the intergalactic medium, which varies from region to region across the cosmic web. In denser environments, jets are confined and cannot grow as large. In sparser environments, in the voids between filaments where the intergalactic medium is thinnest, jets can expand with minimal resistance. If there exists somewhere in the unobserved universe, a supermassive black hole embedded in a galaxy sitting in an unusually sparse region of the cosmic web, With just the right accretion rate and just the right jet orientation, its radio structure could potentially extend to scales we've not yet observed. The records that Alcyoneus and Porphyrion set may be records only of our current observational capability, not of the universe's capacity for construction. And our observational capability is about to increase dramatically. LAW, the instrument responsible for nearly every giant radio galaxy breakthrough of the past 5 years, has mapped only 15% of the northern sky. The full survey, when complete, will cover the entire northern hemisphere at sensitivities that dwarf. Earlier radio surveys, every previous expansion of LOAR coverage has revealed new giant structures, new record holders, new populations of objects that were invisible to earlier instruments. There is no reason to expect this trend to stop. The remaining 85% of the northern sky almost certainly contains giant radio galaxies that surpass everything currently known. But LAW itself will eventually be surpassed. The Square Kilometre Array, or SKA, is an international radio telescope project currently under construction across sites in South Africa and Australia. When completed, it will be the most sensitive radio telescope ever built, with a total collecting area of approximately 1 square km and a sensitivity that exceeds LAW by an order of magnitude. The SKA will survey the entire sky, both hemispheres, at frequencies and resolutions that make current instruments look primitive. It will detect radio lobes so faint and so extended that they are invisible to every existing telescope. If giant radio galaxies are as common as LAW's partial, surveys suggest, the SKA will discover them in the hundreds of thousands. It will map the full population of giant jet structures across the observable universe, revealing for the first time the true statistical distribution of the largest galactic structures in existence. What that distribution looks like is one of the most consequential unknowns in extragalactic astronomy. If it has a sharp cutoff, a maximum scale beyond which jets simply cannot grow, then the current records are close to the physical limit. If it has a long tail extending to sizes significantly larger than anything yet observed, then the universe contains structures of galactic origin that we have not yet imagined. The data needed to distinguish between these possibilities does not yet exist. It is waiting in the unobserved sky, encoded in radio photons that have been travelling through intergalactic space for billions of years, carrying information about structures so large that the galaxies at their centres are invisible specks within their own creations. This is what separates this story from a simple exercise in big numbers. It is not just that the largest galaxies are large, it is that the concept of largest resists closure. Every answer we give comes with a caveat. IC1-1101 is the largest visible galaxy, but the boundaries of its halo are ambiguous. Porphyrion has the largest measured radio structure, but its record lasted only months before being surpassed. The largest galaxy ever found is a moving target, and the direction it moves is always upward. And beyond the question of individual records, there is a deeper and more unsettling realization. The existence of these structures changes the way we must think about what a galaxy is and what role it plays in the universe. For most of the history of astronomy, galaxies were treated as discrete objects, islands of stars separated by vast empty spaces. The space between galaxies was considered largely inert, a vacuum populated only by sparse intergalactic gas and the invisible scaffolding of dark matter. Galaxies were the actors. The space between them was the stage. But giant radio galaxies dissolve this distinction when a single galaxy's jets span 23 million light-year, threading through the cosmic web, magnetizing the intergalactic medium, heating gas in neighboring filaments. The galaxy is no longer confined to its own island. Its influence has leaked out, contaminated the space between structures, blurred the boundary between actor and stage. Aoi and his colleagues wrote that their findings suggest supermassive black holes do not only hold sway over the galaxy, but also over the cosmic web that surrounds them. This is not a minor addendum to our understanding of galactic physics. It is a fundamental reframing. Galaxies are not just objects within the cosmic web. Some of them are architects of the cosmic web, shaping its properties across scales that rival the web's own organizational structure. Consider what this means for the Milky Way. Our galaxy is a normal barred spiral with a modestly sized supermassive black hole. Its radio lobes are small by the standards of giant radio. Galaxies. Its influence extends in stellar terms only a few hundred 000 light-year. In the context of the cosmic web, the Milky Way is a mote, a single node in a filament gravitationally bound to a small group of neighbours, falling slowly toward the Virgo cluster along with the rest of the Lanier supercluster. Our galaxy's influence on the large-scale structure of the universe is negligible, but the Milky Way's insignificance at these scales goes deeper than mere size. It is structural. At the scale of Furion's jets, our galaxy is not merely small, it is invisible. If you could somehow view the full extent of Porphyrion's radio structure from a distance sufficient to see both lows at once, the Milky Way placed anywhere within that structure would be undetectable. Not faint, not small, undetectable. A galaxy containing 400 billion stars, a supermassive black hole. Spiral arms spanning a 100,000 light-year, and it would register as nothing. A fluctuation below the noise floor, the structure we call home, the galaxy we have spent centuries studying, the cosmic address we used to locate ourselves in the universe, would be lost in the plasma like a single bacterium floating in an ocean, not marginalized, not diminished, erased. This is not a poetic exaggeration. It is a direct consequence of the numbers. Porphyrion spans 23 million light-year. The Milky Way spans 200,000. The ratio is roughly 115 to 1. If Porphyrion's radio structure was scaled to the length of a football field, the Milky Way would span barely a single yard of the total distance. Our entire galaxy, with all its stars, all its planets, all its civilizations that might exist, reduced to a single stride on a playing surface. You would need a full minute to walk from end to end. That is the scale we are dealing with. That is what the universe has demonstrated it can build from a single galactic source. And here is the part that makes this personal in a way that abstract numbers never can. Every measurement humanity has ever made of the cosmos has been made from inside the Milky Way. Every telescope, every space probe, every photon we have ever collected has arrived at instruments located within our galaxy. Our entire understanding of the universe is built on observations made from a platform that at the scales being considered barely qualifies as a location. We're not observing the cosmos from a meaningful vantage point. We're observing it from a pixel, a single unremarkable pixel in a structure so vast that the structure itself is unremarkable compared to what the universe can build. Every astronomy textbook, every map of the cosmic web, every diagram of the observable universe, all of them place the Milky Way at the center because that is where the observer is located. But the centrality is observational, not physical. There is nothing special about our position. There is nothing special about our galaxy. There is nothing special about the filament we inhabit or the supercluster we belong to. We are an average galaxy in an average location. and the only reason the universe appears to radiate outward from us is that light takes time to travel, creating a spherical observational horizon centered on wherever the observer happens to stand. An observer in IC 1101 would see a different observable universe centered on a different point containing different galaxies at different distances. An observer in Porphyrion's host galaxy would see yet another. Every location in the cosmos is the center of its own observational sphere, and none of them is privileged. But IC 1101 sitting at the center of Abell 2029 shapes the thermal properties of its entire cluster. Its black holes' past activity influenced gas dynamics across millions of light years. Its gravitational dominance accreted material from the cosmic web along the axis, connecting its cluster to the neighboring Abell 233. It is not merely embedded in the cosmic web, it has consumed enough of its local web to become the dominant feature of its own cosmic neighborhood. And Porphyrion, with its jets reaching 2/3 the radius of a cosmic void, does not merely sit in the web. It reaches across the web. Its outflows interact with the intergalactic medium on scales that rival the voids themselves. A single galaxy's black hole pumping energy into space at the rate of trillions of suns, sculpting the magnetic field of the cosmos across distances that dwarf everything we have ever called large. This is the emotional core of the story, not the numbers, not the records, not the debate over which galaxy is technically the biggest. The emotional core is the realization that galaxies can become so large and their influence can extend so far that they stop being things inside the universe and start being things that shape the universe. At the extreme end of the scale distribution, the distinction between a galaxy and a cosmic structure begins to dissolve. The galaxy does not merely occupy a position in the cosmic web, it modifies the web. It reaches across the voids, it touches other filaments, it injects energy, magnetism, and heat into regions that were supposed to be empty and inert. The Milky Way is enormous. Andromeda is larger. IC 11101 is vastly larger still, and the giant radio galaxies extend to scales that make even IC 1101 feel contained and local. Each comparison erases the emotional weight of the previous one. Each new rung on the ladder diminishes everything below it, and the ladder, as far as we can tell, has no top. There is a specific kind of cognitive vertigo that arrives when you follow this ladder all the way up. It is not the same as the awe you feel looking at a photograph of a galaxy. That awe is comfortable. It is the vertigo of realizing that the cosmos has no obligation to remain within the boundaries of your imagination. You can build a mental model of the Milky Way. You can hold it in your head as an image, a concept, a thing with a shape and a size. You can do the same for Andromeda with effort. You can even do it for IC 1101 if you anchor it to the comparison with the local group. But you cannot hold Porphyrion. You cannot visualize 23 million light-year of relativistic plasma extending from a single point source into the void. Between cosmic web filaments, the image does not fit. The frame of reference you need does not exist in human experience. The structure is real, measured, confirmed, but it exists beyond the threshold of what our evolved cognitive architecture can render as a picture. And that failure of visualization is not a weakness of science communication. It is the point. The universe at these scales is not supposed to make intuitive sense. It was not built for human comprehension. It was built by gravity, by thermodynamics, by the relentless physics of accretion and ejection operating over billions of years without any awareness that a species on a small planet in a minor spiral arm would one day try to picture what it had done. The structures exist whether or not we can imagine them. The lows expand whether or not we can feel their size. The galaxies grow whether or not we have words adequate to describe them. The terrifying size of the largest galaxy we've ever found is not a single number. It is a spectrum. At 1 N sits IC 1101, the anchor, the visible giant, the most extreme expression of assembled starlight ever observed, a galaxy whose stellar body and halo span millions of light years and whose black hole ranks among the most massive objects in the cosmos. At the other end sit the giant radio galaxies Alcyoneus and Porphyrion, and the unnamed structures still waiting to be detected in the unobserved sky, whose physical extents reach tens of millions of light years, and whose influence extends to the architecture of the cosmic web itself. Between these two endpoints lies the ambiguity of definition, the honest acknowledgement that largest depends on what you measure, and that the universe refuses to provide a single clean answer. But the ambiguity does not weaken the story, it deepens it. Because the truly terrifying realization is not that one specific galaxy is big, it is that the universe can produce galactic structures so vast across so many different axes of measurement that even the galaxies we already treat as immense. The Milky Way and Andromeda and Messier 87 and every other galaxy we have ever photographed and studied and named begin to look local, begin to look small, begin to look like details in a picture whose full extent we've not yet seen and may never fully see. The Milky Way is not a large galaxy. It is a speck orbiting inside a supercluster that is itself a minor feature of the cosmic web. Andromeda is not a giant, it is one island among 2 trillion in an observable universe that may represent less than 1% of total cosmic volume, and even IC1, the most visually extreme galaxy ever measured, sits at the centre of one cluster in one filament of a web that stretches across 93 billion light-year of observable space, and likely extends far beyond. The largest galaxy we have ever found is not a settled answer. It is a question that keeps expanding just like the structures it describes. The records will keep falling. The instruments will keep improving. The 85% of the sky that law has not yet surveyed will yield structures that surpass everything in current catalogues. The square-kilometre array will peer deeper into the radio universe than any instrument before it, mapping populations of giant jets that are currently invisible, and each new discovery will push the upper end of the distribution further outward, further from human intuition, further from any framework that allows us to feel the scale rather than merely calculate it. And the real terror is the dawning recognition that our sense of cosmic scale, the framework we use to make the universe feel navigable, was never adequate. It was a simplification, a story we told ourselves to make the darkness feel manageable. And at the extreme end of galactic size, where stellar halos blur into intracluster light and radio jets span the distances between cosmic web filaments, that story quietly falls apart. The universe builds galaxies so large that other galaxies stop being useful points of reference. So large that the concept of a single object begins to strain under its own weight. So large that the boundary between galaxy and cosmos becomes a question without a clean answer. That is the terrifying size of the largest galaxy we have ever found. Not a number, a feeling. The feeling that arrives when you climb the ladder of cosmic scale far enough to realize the ladder itself is the smallest thing in the room.